This work presents preference-based learning for user-guided HCD gait generation on bipedal walking robots. We propose the use of preference-based learning towards identifying the essential constraints that optimize the underlying preference function of the human operator in as few iterations as possible. In each iteration, new actions are sampled via Thompson sampling. Gates are then generated for these actions and executed on the robot. A human operator observes the experimental performance and provides a pairwise preference. The learning framework then updates its belief of the optimal action using this new preference information, and the process is repeated. We experimentally deploy this framework on the planar biped Amber 3M to learn 5 essential constraints: average forward velocity, minimum foot clearance, the timing of this foot clearance, impact velocity, and step length. The combined framework was first demonstrated on Amber 3M with rigid point feet. In each experimental iteration, the algorithm updated its belief of the utilities associated with each set of constraint values, and the experimental behavior of the robot gradually improved. At the end of the 30 iterations, the set of constraint values believed by the algorithm to maximize the user's underlying preferences resulted in experimental walking that was stable, robust to perturbation, robust to treadmill speed, visually appealing, and efficient. To highlight the power of the learning method, the procedure was repeated on Amber 3M with unmodeled compliance at the feet, which is challenging since historically achieving compliant walking has required complex models. The framework was run for 50 iterations, and as before, the experimental walking gradually improved with each iteration. And again, the set of learned constraint values resulted in experimental walking that was stable, robust to perturbations, robust to treadmill speed, visually appealing, and efficient. In general, Line CoSpar NLP was able to learn in relatively few iterations 2 different set of essential constraint values that resulted in stable, robust, and natural experimental walking without the need for manual parameter tuning. We would like to thank our sponsors for supporting our work. Thank you.